So for number 6, we have photons of wavelength 468 nanometers on a metal surface. We know the kinetic energy of the emitted electrons, the max kinetic energy, is 1.8 eVs, and we can use that with kinetic energy max is the photon energy, which in terms of wavelength is hc over lambda minus the work function. So AI is solved for the work function. Of course, with hc over lambda, h is in joule seconds, so we're going to need to convert as well. So we have hc over lambda minus the work function, so the work function is hc over lambda minus E max. And so we have h and c, and we have lambda right here with the joules to electron volt conversion. So that's hc over lambda minus the 1.81. Where are they getting 1.81 from? They said 1.8. That's interesting. All right, whatever. And that gives us 0.85625, which is roughly 0.86 EVs. Incidentally, that set up there gives you 2.65625 EVs. So that minus 1.8 rounds to 0.86 EVs. So AII wants the longest wavelength that will eject an electron from the surface. Longest wavelength is actually the least energy, so that would have a kinetic energy of roughly 0. So if kinetic energy is hc minus the work function, and kinetic energy is 0, that must mean that hc over lambda equals the work function. We know the work function from AI, and we know h and c, so we just have to solve for lambda. Lambda is hc over the work function. There's a definite typo here in the mark scheme. When they show the work, they put the wavelength in. They're not looking for wavelength. They need to put in the work function. So we have h, we have c, we have the 1.6 times 10 to the negative 19 to get from EVs to joules, but we need the work function in EVs, not the wavelength. So yeah, there's the work function with the EV to joule conversion, but the math is right. So they just wrote the wrong thing, but we get 1.45 times 10 to the negative 6 meters. That's the right answer. Okie dokie. That one was interesting. They usually ask about the kinetic energy max, highest frequency, shortest wavelength, not the least. So anyway, BI, we're now on B. Alpha particles, kinetic energy 5.9 mega electron volts on lead 207, and closest approach is 4 times 10 to the negative 14 meters. That's an EI question. E1, I should say, not EI. And BII is also E1. Since we just did E1, might as well talk about it. So the charges, they give the charges in coulombs, and that's cute, but I don't really want the charges in coulombs. I actually want elementary charges because it gave me the kinetic energy of the alpha particles. That's what the bottom is there. So, how they actually got this math. So remember that the kinetic energy of the alpha particles on approach gets stopped by the field, so it goes all to potential, and potential energy is kQq over r. And so if we solve for r, the distance of closest approach, we get kQq over the potential energy, which is the kinetic energy. So if we look at this d or r down here, we get kQq over the energy, which was 5.9 mega electron volts. And when you run the numbers, you get about 4 times 10 to the negative 14 meters. Okay. And then once we know that, it says radius of a nucleus of lead is 7.1 times 10 to the negative 15 meters. And it's why are there going to be no deviations in the Rutherford scattering? And that's because the distance of closest approach, so yeah, if the lead radius is 7 times 10 to the negative 15, and the closest approach is 40 times 10 to the negative 15, then the alpha particles really don't get close to the nucleus. So if they don't get close to the nucleus, 1, 2, the strong nuclear force will not have an effect because the alpha particle is not close enough to the nucleus. All right, number 7. Just as a side note, it's what do you mean it's not close enough? What is close enough? Keep in mind that the strong nuclear force works at a range about the size of the nucleus itself. So we're talking 10, an order of magnitude away, 10 times further away than the size of the nucleus, and it's just not close enough. All right, so that's about 5 minutes for number 6. Let's do number 7. at 15 minutes per video. Maybe we'll get 3 problems done. Let's see. So number 7 says that the stopping voltage for the ammeter is 1.4 volts. And so 7a starts off with saying what exactly is the photoelectric effect. So photoelectric effect, you have electrons ejected from a surface of a metal that light is shining on, and those electrons gain that energy from the photons themselves. Not all metals do this, and in the metals that do this, you have to overcome the work function of that metal. So that's why it says there is a minimum threshold energy or frequency or maximum wavelength that you need in order to overcome the work function. And so 7b says maximum velocity of the photoelectrons is 700 kilometers per second, and we know that the stopping voltage is 1.4 volts. Well, so yeah, kinetic energy maximum is hf minus the work function, but it's also 1/2 mv squared, and it's also qv. So if we're talking about maximum kinetic energy, that would be qv stop, and it would also be the maximum speed, which is what we're looking for. So really what I want from that is, so the max velocity is radical 2 qv stop divided by the mass of the electron, which is what this expression says right here. 2 times q, 1.6 times 10 to the negative 19 coulombs, times the voltage divided by the mass of the electron, and we wind up getting about 702 kilometers per second. Specifically, we get 701.646 meters per second. And here we have 7c saying that the photoelectrons are emitted from sodium. It has a work function of 2.3 EVs. Calculate the wavelength of that radiation on the sodium. Alright, so we know that maximum kinetic energy is Q times the stopping voltage, which is HC minus the work function, H over lambda minus the work function. Q is an electron, so Q is E. So that QV stop, the V stop is 1.4 volts. So that's where the 1.4 EVs comes from in the mark scheme. And the work function is 2.3 EVs, so we wind up with HC over lambda equals the QV stop, the 1.4 EVs, plus the work function. So when you solve for lambda, you get HC over QV stop plus the work function. And so that's what we have right here in the mark scheme. There's H, there's C, here's the sum of the 2.3 and the 1.4. So that's where the 3.7 is coming from. But we're going to need a joule to electron volt conversion because H is in joules, not EVs. So when you run that all through, you get 3.4 times 10 to the negative 7 meters, or 340 nanometers, which checks out. That's the actual number that you get. When you round it, it's 3.4 times 10 to the negative 7. Okay, we're doing good on time. Let's move to number 8. Okay, so 8 is interesting. It says that there are 2 metals, P and Q, and 3 different radiation sources of increasing wavelength. Let's note that increasing wavelength means decreasing energy, and each of these metals, P and Q, has and this page breaks in the typical weird stacking fashion over here. Okay, so the photon transfers its energy to the electron. The kinetic energy of AIII. Why does radiation B give different results? Because radiation B has a different wavelength. I don't really love this question, AIII. It says radiation B gives different results. Different results than for radiation A, or different results for the two different plates. I mean, we can give both reasons. One, P's work function is going to be different than Q's work function. That has to be for if electrons are emitted from one metal and not the other for the same wavelength. So yeah, if like one metal has enough kinetic energy for the electrons to be emitted, but the other metal does not, for the same hc over lambda, the work function must be different for the two of them. But also, the reason why, I don't know, it says different results. Radiation A, nothing is emitted. Radiation B, at least something is emitted. And the reason why is because radiation B has a shorter wavelength than radiation A does. So that's two reasons why. Anyway, B. Why is there no effect on the table of results when the intensity of source B is doubled? And that's because the table of results... Okay, so B. Why is there no effect on the table of results when the intensity is doubled? Increasing the intensity increases the number of photons, but it doesn't change the energy of the photon. So if you're already emitting photoelectrons at a certain frequency and certain voltage, then you increase the intensity, you're going to get more photoelectrons that are like kind of being emitted at that point, but it's not going to, it's going to, like, because you're getting more photoelectrons because you're hitting it with more photons. You're not going to get more photoelectrons to pop off the surface, because whether or not you overcome the work function and the kinetic energy of the electrons themselves has everything to do with the frequency or the wavelength of the light, hc over lambda. That has nothing to do with how many photons are striking the plate. So that is B. Then we have C. C is pretty basic. It says that the photon energy gives the Ke max of the electrons and what's the work function. So Ke max, we slip that in. The hc over lambda, which is the energy of the photons, we slip that in. The 1.1 times 10 to the negative 8, and the difference between them is the work function. So that's 1.1 times 10 to the negative 18 minus 5.1 times 10 to the negative 19, which is what this says over here. And because reasons, they want the work function in electron volts, so they have the joule to electron volt conversion in here, so we can get the answer in electron volts. In joules, the answer would be 5.9 times 10 to the negative 19 joules, which is 3.6875 EVs. Okay, and that was number 8. We had 13 minutes. Maybe we can sneak in number 9. Compton scattering. Good. I was getting sick of the photoelectric effect. So, de Broglie wavelength lambda of a particle is hc over the energy. That's also for a light photon, but that's all particles. So E equals hc over lambda, so lambda is hc over E. Great. The beam of electrons of energy 4.2 times 10 to the 8 EVs is produced in the accelerator. Beam of electrons. So now we know the energy, we could figure out the wavelength. All right, so electron beam studies nuclear radius of carbon-12. It's directed from the left at carbon-12. Detector is placed at an angle theta relative to the direction of the beam. Graph shows the variation of the intensity. With theta, there's a minimum for theta equals theta naught. Where's the graph? There's the graph, so we see a dip in the graph. That must be a, what do they call it? It is a minimum. Let's remember that this electron graph is a representation of the single slit diffraction, and so we're looking at just this portion of that graph. Now, A actually has nothing to do with the graph. It says show that the wavelength is about 3 times 10 to the negative 5 meters, and we're using the formula that I gave you before from E equals hc over lambda. We have H, we have C, we have the energy in electron volts, and we have the electron volt to joule conversion because H is in joule seconds. We get 2.96 times 10 to the negative 15 meters. BI, how the results of the experiment provide evidence for matter waves. The fact that the electrons are showing a diffraction pattern, and only waves diffract, so that must mean that a particle is acting as a wave. All right, I kind of showed that before. I'm going to go over my 15 minutes, but that's okay, we'll be close. All right, BII. BII is actually single slit diffraction. It says the diameter of the carbon-12 nucleus is 4.94 times 10 to the negative 5 meters. What is the angle at which the minimum is formed? If you remember from single slit diffraction, theta is lambda over b. So here's our lambda from before, and b is the slit size, or the size of the object causing the diffraction. And so we have sine of theta is 0.599. It's actually sine of theta is lambda over b, and we get rid of the sine for very small angles. But the, so 0.599, which is 37 degrees, or about 0.65 radians. BAAA wants to know why electrons with energy of approximately 10 to the 7 EVs would be unsuitable for the investigation of nuclear radii. And Merck's team says de Broglie wavelength is much longer than the size of the nucleus. Why does that matter? Because to get diffraction, you need the wavelength to be roughly the size of the gap or object that you're diffracting through or around for diffraction to happen. So you would get no diffraction pattern. Now, how do we know that from 10 to the 7 EVs? You're going to have to calculate the wavelength. They didn't show that. You wind up getting 1.24 times 10 to the negative 13 meters, and it says the diameter of carbon is 5 times 10 to the negative 15 meters, so that wavelength is way bigger than that, and that's not going to fly. So no diffraction. Okay. And this part is actually an E1 question. The formula they're making reference to is that the radius of an atom is the Fermi radius times the nucleon number to the 1/3. I feel like we've seen this question before, but it says show that the density of a nucleus is the same for all nuclei. So we know that density is mass over volume, and the mass of a nucleus is the mass of one nucleon times A, being the atomic number, the number of nucleons in the nucleus, and volume of a sphere, it's spherical nucleus, 4/3 pi r cubed, and if r is r naught a to the 1/3, then when you work it all out, a to the 1/3 raised to the third just becomes a. And so the nucleon count, the number of nucleons in the nucleus, cancels out. And so I don't care what your atomic number is, the density of the nucleus is going to be the same for all nuclei, because a cancels out. All right, we have two more questions. We have numbers 10 and 11 hanging out down here, but I am past my 15-minute limit. I do not want to hit 20 minutes, and so I am going to cut this and make the last video later. Thank you.